Hello, today I'd like to tell you about an algorithm I came up with in order to sample from some quantum spin systems. I'm excited about it because I recently realized it coincides for some but not all parameters with what physicists came up with for numerical simulations, so that tells you it can't be too bad. And the advantage of this formulation, however, is that it allowed me to use lots of different tools to rigorously prove results that I now want to show to you. So let's start with the setting. Typically, we consider some quantum spin system on some graph G. Think of set 3, for example. And to each edge, we attach a periodic time interval of length beta, where beta is the inverse temperature for the system. Then we consider Poisson point process rho u that drops links. Each link is either a cross with probability u or a double bar otherwise. And if we now weigh each such link configuration by 2 to the number of loops, then we obtain a probability measure in the space of link configurations. So a loop is obtained as follows. Let's say we start at this point here, then we go in any direction we want until we encounter a link. Crosses are traversed like this. Now, if we get to the end of a time interval, then we make use of periodic boundary conditions. We traverse across again. Double bars are traversed like this, so the only difference is that you change directions and then you end up where we came from. So this is one loop. Another loop would be this, for example. Okay, so how does this relate to quantum spin systems? The idea goes back to Tod Eisenman-Nachtigall and Daniel Ulci, and it basically tells you if for any 2 points, vertices x and y, there is a positive chance uniformly in the system size that they are in the same loop, then this corresponds to long-range order for some spin-1/2 quantum Heisenberg magnet, which might be the ferromagnet, the XY model, or the antiferromagnet for different values of U. Okay, so let me first describe my first attempt how to sample from the system. So this will serve as benchmark to beat, which is some kind of Glauber dynamics. So without going too much into details, the idea is to just look at a tiny bit of space time, and we then resample this tiny bit of space, this link configuration at this tiny bit of space time, according to the measure we want to sample from, conditioned on what's going on outside of that interval here. Now, kind of by design, this updates at most one link, but how many operations does it take to update this one link? So recall in the measure we want to sample from, we have this 2 to the number of loops. So if you are familiar with Glauber dynamics, you know that the least you'll have to do is you'll have to be able to tell if adding or removing a link will increase or decrease the number of loops. So if a loop is very long, this takes up to order volume many operations. If loops tend to be small, you'll be able to get away with O1 many operations or anything in between. So what's a better way to sample from this measure? It is kind of analogous to the Swenson-Bong dynamics. So we decorate our state space. So instead of only considering link configurations omega, we also consider coloring C. So these coloring C is said to be compatible with a link configuration omega if the color on each loop is constant. So to each loop, we assign exactly 1 out of 2 colors. This gives us a freedom of 2 to the number of loops, hence getting rid of this factor here. And what we get in return is, however, this requirement that coloring needs to be compatible with omega. So you see here, one loop has 2 different colors, so that's not admissible. So it is not compatible. So what are the dynamics? The dynamics are obtained by these 2 steps here, which is really just going back and forth between the link coordinate and the color coordinate, and then sampling from this measure here. So by design, these dynamics leave mu invariant, and we satisfy all the conditions to apply the ergodic theorem. So this tells us that the omega marginal converges in total variation to the measure we want to converge to, because the omega marginal of mu is pu, the measure we're interested in. So I don't want to go into the details here, but of course you might be concerned about this going back and forth between the link and color coordinates being very computationally expensive. But given the link coordinate sampling decoloring really only takes at most order of volume many operations, because everything can be done locally. You just trace out each loop. You have to do that only once, and you assign to each loop an independent color. The trickier part is to see that given the coloring C, the link configuration can be sampled efficiently. So I don't want to go into the specifics here again, but the key idea is that everything factorizes surprisingly nicely, and you end up with essentially a somewhat restricted product measure. So again, this only takes order of volume many operations. So just to summarize, the number of links updated in these better dynamics are always going to be of order of the volume of the system. The number of operations to do so for one step is also order volume of the system. This is just a slide before. Now for Glauber dynamics, we update at most one link, and the number of operations needed to do so can range from order 1 to order volume of the system. So now you would expect that if you take order volume many steps of Glauber dynamics, so then you update order volume many links, this might or might not be roughly, this might or might not mix roughly as much as one step of these better dynamics here. So I can only prove one direction here, which and the amount it mixes, so to say, is of course like not given by the number of links updated. That's a poor proxy. Instead, better way to actually understand mixing is by a comparison of the largest eigenvalue or the spectral gap. So, and indeed, this is what you can prove. The largest eigenvalue of order of volume many steps of Glauber dynamics is less or equal than the largest eigenvalue of these better dynamics up to a small additive mistake that vanishes as you send the system size to infinity. So intuitively, this tells you that one step of our algorithm can't mix more than order of volume many Glauber steps. And this is a very general proof using some interpolation between Glauber dynamics and Auer dynamics in the spectral decomposition, which is quite explicit, which is inspired by some Boolean analysis. And it can also be used to prove some interesting, rederive some interesting results about Swenson-Lang algorithms and comparisons to Glauber dynamics, which goes back to Ulrich. So is there anything we can say about mixing times? So mixing times is a bit harder to define, but instead what we can look at is bound. So if we take t steps with our better algorithm and we started omega naught, how far are we away from the equilibrium measure in total variation? And this can be bounded if the degree is finite. So for example, on set D, this is finite. And for high temperatures, so beta sufficiently low, then there exists a gamma less than 1 such that we have this geometric decay here with some constant in front of it that might depend on the initial configuration. And the conjecture is that, as a matter of fact, like under the same assumptions, this holds for all beta. But this is quite hard to prove in general. So is there anything we can say about lower bounds and mixing times? So we have, I was able to derive Lie-Sokal type lower bound and autocorrelations. So this expression here is just the autocorrelation, and this can be bounded from below by something that is relatively big if the variance of the number of links in the equilibrium measure is big. So, okay, now consider this implication here. If you have a small mixing time, then you necessarily have a small autocorrelation time. So now you might hope to obtain some lower bounds in the mixing times by essentially considering the contrapositive. So big autocorrelation time, which according to this bound you get if the variance is big, should imply a large mixing time. So large mixing time is equivalent to a small spectral gap, of course. So this we can do under one additional assumption. So the first assumption here essentially tells you that the variance of number of links is big. And then under the additional assumption that we really have separated phases, then we can use some isoperimetric inequalities to prove that the spectral gap decays exponentially in the system size. So this means we have really slow mixing. And this is all I wanted to tell you. So thanks for listening.